Let's talk about dimensionality reduction. This is a super important topic. If you think about a Tesla, you got a camera looking out the front for maybe 4K by 4K of images and maybe 30 or 60 frames per second. All that data is coming in. And you have to make a decision like, am I about to ram into a car? Find an object, decide if it's in my way, decide if I have to steer around it, and you don't have much time, like 1 second to do that. You can't possibly process all those pixels in that short amount of time. And by the way, your brain can't do it either. If I throw a baseball at your head, your eyes will figure out it's going to hit your head and your head will jerk out of the way in a really fast time, like 50 milliseconds. So you don't do that by processing all the pixels in your visual system and determining it. What you do is you do dimensionality reduction. I think it's the reticular formation in your brain focuses attention on things that matter and ignores 99% of the data coming in your senses. And there's a famous psychological demonstration where they have students playing basketball, and then they have a guy wearing a gorilla suit drive a unicycle right through the basketball game. But people that have been told, count how many times the basketball is passed, don't see the gorilla at all. It's a famous test. If you're paying attention to something, then you are not seeing anything else. And that is what you must do. That is what all machine learning models must do. And here's a mathematical way to see how important that is. Let me clean off this old stuff. And consider this. If I have a cube, if I have a graph that goes, say, from 0 to 1, and you say, how many points would it take to trace the behavior of a function there? You'd say maybe you need to have 10 points across the range from 0 to 1 to trace out a curve. And so here's another way to look at it. If I choose 1,000 points at random to sample something in 2 dimensions, then only 25 of those points are on the edge being defined as in 1% of one of the edges. So most of the points are in the middle, tracing out the shape. But as dimensionality goes up, more and more of the points are on the edge. If I'm in a 100-dimensional space and I put in a point, it has 100 random coordinates, and one of those is very likely to be very close to an edge. So if you get up to even 1,000 dimensions, which is nothing, consider every pixel would be a dimension, then all the points are on the edge of your hypercube. They aren't in the middle. So you can't possibly trace out the behavior of any function with any reasonable number of points. You could never have enough data to possibly describe the behavior of whatever you're measuring. And that's because, as mentioned before, those pixels are not really independent. If you have 784 pixels in a 28 by 28 image, you really don't have 784 independent things that matter. All you want is to find foreground, background, the edge of an object, things like that. That is many fewer dimensions. So even though you might have a camera giving you 4K by 4K at 30 frames per second, you really want to extract much less information out of that. All you want is there a car in front of me? How close is it? That's all you want. You don't want all that unthinkable amount of data. So you have to lower it, lower the dimensions. And here's another way to look at it. Consider this. If I make a hypercube that goes from 0 to 1 in many dimensions, I can ask how far apart are two random points. And so I pick two random points and figure the distance. In 2 dimensions, 2 points are separated by 0.5, but in 100 dimensions, they're separated by 4. In 10,000 dimensions, they're separated by a distance of 40. So even though the dimensions only go from 0 to 1, well, my points are separated by 40. So it again shows you I cannot possibly have enough information to ever model the entire behavior of anything I'm measuring at that level. And so that shows that you must reduce the number of dimensions. And how do you do it? Your brain has a reticular formation that does something to try to find things that matter. But in a machine learning model where we don't have preconceived notions like that, we use this thing called principal component analysis. This is the standard way you do it. And so here's how it works. I'm going to import those MNIST handwritten digits again. So we get these. And then I'm going to choose the right number of dimensions. What happens is you take the images and you take all the information from them and plot them in a high dimensional space. These have 784 pixels in each image, so you plot them as a point in a 784 dimensional space. And then you plot all the images and you see they're not going to be randomly scattered through that space. They're going to fit on a hyperplane. There's going to be some trend, and you find the hyperplane that passes through them to capture the most variation. And that's what this does. This is what principal component analysis does. It says out of those 784 parameters, how many of them are actually needed to explain the variation in these images? And so here, I'm going to find out how many parameters I would need to capture 95% of the variance. I started with 784 dimensions, but I only need 150 of those dimensions to capture 95% of the variance. All the rest don't really matter. So that's useful information. And so you can now use principal component analysis to create a model that does not use all the information in the images, but just the principal components. And here, it uses a randomized search to find a good combination of the hyperparameters, deciding what the best thing to do is. And what it concluded is you can use 465 decision trees and only 23 dimensions. And that gives you an 85% accuracy at discriminating those images. So you took the 784 dimensions and combined them to form 23 parameters, which are all you need. And I don't know why it's taken so long. It's doing this fitting. All right, take a while to fit. So now you can now see the effect of reducing it. You can see graphically what it looks like. And I guess this has taken too long. I'll just, wow, it seems to froze up on me. Okay, anyway, here's what you see. Here's the original images. Here's the image that includes only the 24 parameters.
PCA is a very heavy algorithm, so usually it takes time.
Yeah, yeah. Anyway, you see, this is what was left. And you see it has blurred it out, but it kept enough that you can still recognize the images. So this is what it actually uses. This reduced amount of information is what it actually works on. And the same thing happens in your brain. So this is a very important concept, dimensionality reduction. And the last one, let me make a separate video of it.